All right, your home plate for tonight is on pages 303, 304. 303, the whole page, and from 304, only number 11. Page 303 and number 11 from page 304 only. All right, our objective for today, I can multiply polynomials. Once again, I can multiply polynomials. We're still within the umbrella of multiplication. Today we're going to add a couple more things just to put together some concepts that we need to cover. But overall, by now, we should know the definition of polynomials. Is that correct? So we don't need a Freire model. So tell your neighbor the definition for polynomials, please. All right, very good. I heard monomials, or the sum or difference of monomials. Is that correct? Yeah? And we know what they look like. We know what they don't. Hashtag, and so on and so forth. Okay? So from there, we got into some of these polynomials, multiplying polynomials. We covered three different types. We covered distributive property. We covered area model. And then yesterday we revisited what is vertical multiplication, which is stuff we've been doing since elementary, yeah? And we did some of those. From there, we got into the different patterns, three different patterns that we know for most common patterns in polynomials. So, lock your toolbar. Without looking at your notes, write in there 1, 2, or all three of the most common patterns. Without looking at your notes. You got 40 seconds. Ready? Go. All right, tell me whatever you have. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Time. All right, I see some of you. Oh, bam, look at some of you. Let's go. So yeah, the most common patterns are the following. They're known as what? Polynomial identities. There's more, but those are the most common ones that we work with. You need to know those, guys. So once again, make sure you put those as a mental note. So from there, I said, how do we know their identities? Is that each side is identical to the other side. So how do we do or make sure that that's true? By verifying. So we verify that it's a identity. How do we do that? Multiply, simplify, and make sure each side is equal to the other. We did that, and the other. And for home play, you had some of these where it was more elaborate. You needed to multiply, simplify, and so on and so forth. From there, we moved on to rewriting numbers. Remember these? Yes? Writing them as binomials. And then from there, we went into multiplication of those, rewriting them with identities. We got to that, and the other, and we got to that. Right? Yeah. Okay. So that brings us for today what we're going to do today. So I need your attention, please. So here it goes. As you know, each one of us has a different focus in our noodle, in our mind, in our brain. Now, some of you love mathematics, like me. And everywhere we go, we see math. Everywhere. And sometimes we catch ourselves doing math without even thinking about it. We're either counting our steps, thinking about patterns. For example, I went to get an oil change this weekend, and they're like, you can wait in the lounge for your vehicle, sir? Well, all right. So I sat there, and as soon as I sat down, I went like that to relax. I looked up. Guess what I see? the little tile squares from the ceiling, well, guess what I started doing? Finding the area in those tiles. So I'm like, I started multiplying, okay, how many across, how many the width? But then I'm like, wait, but that's not the total because some have light, so I subtracted how many with light. Then I saw some of them didn't have a light but had a circle like that. So I'm like, well, if I figure out the area of that little circle times the many, anyways, that's, that's what was going through my mind. And what I'm getting to is that we have mathematics everywhere. Everywhere. For those of you that are more inclined to arts, well, everywhere you go, you're gonna pay more attention when people are talking about music, or about painting, or about dancing, because you're more into the arts. Some of you like poetry, so where you go to places, as soon as you hear somebody like throwing some lines like, and yeah, and my God, anyway, and then you start paying attention more to the poetry part. However, back in the early 1200s, late 1100s, there was this mathematician known as Fibonacci. He was an Italian mathematician. He discovered that there's patterns to everything in nature. And he saw stuff like this. And he saw that the way plants grow or things in nature involves patterns. Such as us, we have math in us, whether you like it or not. So really, do I hate math? Well, you are math. Boom, simple as that. So guess what? And I said it before, you can go home and try this yourself with your family. Measure the length from the shoulder to the tip of the fingers of their arm, stretched. Divide it by the length of the elbow to the tip of the fingers. You're going to get a number close to 1.618. You're like, what? Yeah. If you measure your height divided by the length from your belly button to the top of your head, guess what number it comes close to? 1.618. There is math in us. Fibonacci found out that there's patterns for everything that grows in nature. And let me show you this shell. This shell, he figured that it has a pattern in growth. There it is. So he said, let me start with the area of this small square here in the center is 1. And then I'm going to put another one just like it next to it, so that's 1. To get the next growth pattern, I need to add the previous 2 to that. So this becomes 1 plus 1. It becomes what? 2. To get the next area, I use the previous 2. So what is 2 plus 1? 3. The next area, what is 3 plus 2? 5. What is 3 plus 5? 8. What is 8 plus 5? 13. So what would be the next growth area here? 21, and so on and so forth. That's what we know as a Fibonacci sequence because of his name. He's an Italian. Now, how does that relate to us? Well, it relates in the sense that we have math in us. Let me show you where we can find it right away. Do you see it? Yes. And how is that important, Mr. Q? Well, don't you have now in technology that you can turn on your phone or your security just by putting your thumb? Computers? But guess what that does, though? It exposes you to hackers, especially hackers that know how to use numbers. Today is December 3rd, today in the morning in the news, and yesterday evening I heard that I don't know if it was the state or the federal government, they were putting out a advisory for consumers, for everyone buying, especially smart TVs, to go to a website to show you how to put security restrictions on your TV, smart TV, and which tape to use to cover the camera on your TV, because hackers are hacking onto your TVs, listening and recording people at home. You're like, what? Oh, yes. You're like, how could that be, Mr. Q? Well, let me explain it in your terms. Imagine that you are at home, and you're like, I'm going to install a door. And you install a door. It's an invisible door, and you only have the key. unless somebody gets a hold of the key. Is that correct? Well, that invisible door is your Wi-Fi. Who's the only one that can get in there? Only you guys with the security, except unless it's a hacker. If they're a hacker, they can figure out patterns on your system and get into your door. They open the door, and now they're in your home. How? They can turn on the mic and the camera on your TV or your cell phone, whatever. Where I'm going is that that's how numbers are used. And that's how companies make their money, by targeting all of us, because we are math. We have math in us. Go ahead, Mr. T, you're scary. Anyway, I just wanted to go over the Fibonacci sequence. That was in the early 1200s. Later on in the 1600s, there was another mathematician. His name was Pascal. Blaise Pascal. He was a French mathematician. He saw that some of these patterns also applied, and he can come up with a figure known as the Pascal Triangle. Pascal Triangle. And it looks like this. Here's the triangle. And he said, if I make all these 1 and I need to fill in values in here, there's a pattern of filling those values. So let me show you. I put some animation, so pay attention. Here it goes. There it goes again. And that's how you fill the Pascal triangle. Now, he said, if I start with 1, and that's using the same idea in regards to pattern, this is going to be my row 0, because that's where my beginning is. That means this row has to be row what? 1. Row 2 is that one. So how do I fill this? I always started with 1 and ended with 1. How do we get this number? By adding the 2 previous numbers. What is 1 plus 1? 2. I'm going to go to row 3. 1 and 1 on the end. How do I fill this? What is 1 plus 2? 3. What is 2 plus 1? 3. Next row what? 4. Row 4 is, start with 1 and with 1. What is 1 plus 3? 4. What is 3 plus 3? 6. What is 3 plus 1? 4. And that's row 4. Pretty simple. Another way of writing it without drawing all these figures, you just do 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So copy this, but I want you to fill in row 5. Row 5. Yeah, you don't have to draw the little hexagons. Just write these numbers. There's the Pascal triangle, and you fill me the last row. Copy that and go. All right, let's see. Row 5. Help me with this one. Chelsea, go.
1, 5, 10, 10, 5.
Hands if you got that. That is correct. That is row 5. This is what we call, once again, a what? Pascal's triangle. Now, you need to know how to write this because it's imperative, or should I say important, for what we're doing today. What Pascal found out is that, how is that related to what we're doing with binomials? Well, look up. He found out that if I have x plus y to the, let's say, 5th power, what do we need to do to multiply this out? We need to write this out how many times? 5 times. And he thought, that's a lot of work. Multiply this times this, we ended up with trinomial. Times this, whatever, and then whatever. And then it keeps growing. It's a lot of work. He found out that he can multiply without doing all this and using the Pascal triangle. So today, we're going to use those 2 things, binomials and the Pascal triangle, so that we can multiply and simplify polynomials. All right? So, with that said, copy this one. Example, Michael Jordan cube. And it reads, find the product using the binomial theorem. What is the binomial theorem? By using binomials and the Pascal triangle. That's what we call it now. When we marry those 2 things and use those 2 things to simplify, it's called the binomial theorem. And then it says, then check by multiplying using any method. Now, At the end, once we come up with a simplification, we need to check. How do we check? If you're not sure, you multiply all the binomials times each other, and it should give you the same thing that we got with the pattern. Okay? Copy that, and I'll show you how to use the binomial theorem. So once again, it says, find the product using the binomial theorem. What is that, Mr. Q? Multiplying binomials using the Pascal triangle pattern. Let me show you the process. Here it goes. Please pay attention to the process because this is going to help you simplify these. Here it goes. Step 1. And repeat that again. Step 1. Step 1, we need to know which row to use from the Pascal triangle. And repeat that again. We need to know which row to use from the Pascal triangle to use that pattern. How do we know that, Mr. Q? We know that by looking at the exponent. What is the exponent here? 3, which means which row am I going to use from the triangle? The third row. So how to know what the third row looks like, Mr. Q? Well, you need to know how to build your Pascal triangle. 1, 1, 1, 1, 2, 1. Let's see. This is row 0. This is, oh, I'm sorry. Let me change color because some of you are saying, where are you getting those numbers, Mr. Q? This is a triangle. But what is this row? 0. This one, 1. This one, 2. Which one do we need? 3, which means 1, 3, 3, 1. That's row 3. So you're just paying attention right now. You'll copy it in a little bit. Now that I know which pattern I'm going to use, this is the pattern that I'm going to use. All these are going to be coefficients in my polynomial. So, here it goes. Everybody ready? All right, write your utensils down. Pay attention, please. I'm going to use different colors so you guys can see each set. Here it goes. To get started, I start with my first number. First number is 1. So I'm going to multiply that times both terms. So 1 times x to the third times negative y to the 0. Some of you are saying, Mr. Q, why didn't you distribute here? Because there's a subtraction here. Remember, we don't do that for those. So that means, check this out. First things first. Notice that this one has to the third. This one has to the 0. What is 3 plus 0? 3. The exponents on both terms need to always add to this number. All right, let me go to the next coefficient. What is my next coefficient? Plus 3 times x. Well, look what happens now. Instead of x to the third, it's x to the second and negative y to the first. See, what is 2 plus 1? 3. Oh, yeah, it still adds to that. Let me go to the next one. What's my next coefficient? 3 again. Plus 3 times x to the first and negative y to the second. And last but not least, I'm going to go to the last one. What's the last one? 1 times x to the 0 and negative y to the third. So hopefully, look what we found out. As long as we have this first one and we know what the coefficients are, the rest of it is easy. Why? Because look, we start off with the first term to the exponent, but then it starts descending after every term. Look at this. X to the third, x to the second, x to the first, and x to the 0. The second term starts ascending, but we need to start from 0. Goes to the first, to the second, and to the third. Copy that, and then we'll do the last step together. All right. So, am I done? No. What is the last step? Usually, for everything we do with polynomials, we simplify. So let's simplify. Look up to the screen, please. There it goes. Now that I have my polynomial already multiplied out, I just need to simplify. Here it goes. Oh, side note, because some of us probably forgot. Any number to the 0 exponent is always 1. Any number. Think of a number, a huge number. Negative 23 million. to the 0 exponent is 1. Or let me see, how about star to the 0 exponent? 1. Any number. All right. The second, any number to the first exponent is the number itself. Any number to the first exponent is that number. All right. You guys remember that? Yeah? All right, here we go. What is negative y to the 0 exponent? 1. So what is 1 times 1? So that leaves us with what? X to the third. All right, let's go to the next one. Look at this. What is negative y to the first exponent? Negative y. That means we end up with a negative again. So what is negative times a positive times a positive? Negative 3 x to the second y. Next, what is negative y squared? Negative y times negative y is what? Positive y squared. So this is going to be a positive. All right, positive y squared. So we end up with what? 3 x to the first y squared. And last, once again, what is x to the 0? 1. What is 1 times 1? 1. So what is negative y cubed? Negative y times negative y times negative y. That's negative y cubed. Or in other words, anytime you have an odd number exponent, and if it has a negative somewhere in there, that term will always be negative. Copy that. And let's see how you do with one of these. Let's see. Parentheses a minus b to the 4th power. You're like, Mr. Q, this is a piece of cake. I know. Choco flan. No. Pumpkin pie. No. You guys had enough pumpkin pie over the place? All right. So let's see. To simplify this one, what is the first thing we need to know, everyone? Which row from the triangle are we going to use? Which row? 4th. So we have 1, 2, 3. We need to go one more. So who can give me the 4th row? Jasmine, go. That is correct. So that means I'm going to use this pattern to write out my binomial or my polynomial after multiplication. All right, so let's see. Let's get started. What is my first number? 1 times what? A to the 4th, parentheses, negative b to the 0. What's my next number? 4. So I do plus 4 to the, what do we know from here now? A to the 3rd and negative b to the what? To the 1st. What's next? 6. 6 to the a what? Squared and negative b to the squared. Next, 4. 4 a to the 1st and negative b to the 3rd. And last but not least, plus 1 a to the what? 0 and negative b to the 4th. You're like, I think I get it, Mr. Q. Yeah, now we just need to simplify. Here we go. Once again, what is anything to the 0? 1 times 1 is 1, so we're left with a to the 4th. What did we say whenever we have a odd exponent here, that the negative is going to be for the whole term? Yes, so it's negative 4a cubed b. Next, what is b? Negative b times negative b, it's a positive, so I'm going to end up with positive 6a squared b squared. Next, this is a what? Odd, so this is going to be a what? Negative 4a to the first, b to the third. And last but not least, this is a 1. 1 times 1 is 1. This is negative b times negative b times negative b times negative b. That's positive b to the 4th. How are we doing? Yes. Uh-huh. Because when we multiply this out, let me show you this. X plus 2, x plus 2. What is x times x? X squared. What's another way of writing this? X plus 2 squared. So which is the only one that's going to have the square? The first term. And that's why on these, we always just put the power on the first term to start with. Yeah, same here. Which is the first term, a. That's why that's a to the 4th. But we're avoiding all the multiplication by doing just the pattern. Yeah. Some of your friends welcome to y'all with these 5s, 4s, 5 4s, 5 4s, 5 4s. Yeah. All right. All right, let's crank it up a notch. Yeah. Now let's use some numbers. Copy this one, example 3. Example 3, x minus 2 cubed. So what is the first question you're going to ask? Which row do I use? What's our row, everyone? Third row. So that means you need to write out your 10, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This is row 0. This is row 1. This is row 2. This is row 3. Now, an easy way of remembering the rows, look up, guys. This one is always 0, but from there on, all these are the numbers of the row. What is this row? 1, this one, 2, this one, 3, the next one, 4, and so on and so forth. Okay? So with that said, we're going to use these as our pattern. All right? Let's see. Let me get someone to help me get started. How about Victor? What's our first number? What is it? Okay, but we start with what? 1 times x cubed times negative 2 to the 0. That is correct. Ask someone? Danica? Close. 3. 3x squared. That is correct. Pass someone. Cindy? To the second. Pass someone. All right. One x to the 0. It went from 3 to 1, 0. and negative 2 to the 0, 1, 2, 3. And if you got something like that, okay, let's simplify. Here we go. What do we know any number to the 0 is? 1. 1 times 1 is 1, so we're left with x cubed. Here's an odd number exponent, and it's a negative, so that means the whole term is going to be what? Negative. But now we have a number. What is 2 times 3? 6x squared. Next, what is negative 2 squared? Negative 2 times negative 2 is positive times 3, 12. Did you see that? 4 times 3 is 12, and we bring down the x to the first. If you don't see it, let me show you this up here. Negative 2 times negative 2, that's positive 4, times 3, that's positive 12, and you bring this down. And last, x to the 0 is a 1. This is an odd number exponent, so the whole thing is going to be what? Negative. And that leaves us with what? 2. How are we doing with numbers? So? Yes. Oh, my bad. Negative 8. Thank you. Yeah. Who's that? Who? Oh. So yeah, Anthony saw here. Yeah, take a shot. Negative 2 times negative 2 times negative 2. 2 times 2 is 4 times 2, that's 8, and it's a negative. Thank you, Anthony. Yeah? Some of your favorites, how come you over these? Using numbers. Okay, 4, 5, 4, 5, yeah. And if you notice, the ones that are a little bit confusing are just with variables, but with numbers, it's just basically simplifying and multiplying to simplify your binomial, okay? And we'll stop right there, all right? So once again, your home play for tonight, log out, please. Your home play for tonight is on pages 303 and number 11 from page 304. All right? There is tutoring today. It's free. Have a good one. See you guys tomorrow. Bye.